Hello, I'm Brandon John, and I'm going to do a quick demo of my 6.888 final project, which is an FPGA-based power side channel attack. So, just for some quick background, there are power side channels in the past which have existed based on an oscilloscope and measuring in line with the power supply and putting yourself right next to the processor, but this requires physical access to be able to get any data out of how much power this processor is taking. So my method here is to use an FPGA. So assuming an FPGA, you have remote access to an FPGA and can upload your own binary or your own bit file, you have the ability to create anything you want. So the goal here is to use what's called a ring oscillator, which is basically just a NOT gate feeding into itself, and is shown on the right. And then some method of figuring out how fast the ring oscillator is oscillating. The idea being the ring oscillator will go faster as you have a higher power at the location of the ring oscillator, and it will go slower as the voltage there is lower. So this being a proxy for having a local oscilloscope, though it isn't quite as accurate by multiple orders of magnitude. So now I'm going to do a quick demo on how this project actually works. I've got this entire thing running on a pink Z2 board, which is an FPGA plus a processor running Linux, which allows me to have a Jupyter notebook and some very convenient access to it. So this first demo is going to be using what I've been calling a power virus, which is basically a whole bunch of cells just turning themselves on and off as fast as they can, which was useful early on for testing that I was actually getting reasonable data. So this particular demo does a high power draw at the beginning for about 4 milliseconds, and then it goes into this alternating mode, and then it goes low power at the end. High power, of course, being a lower frequency. And so this has got a lot of quantization and a huge range of noise. And there's various reasons for that, but it really boils down to I'm only using 5 ring oscillators in total to average them together, and I'm integrating for a short period. In this case, 5 integration cycles. I don't know the exact unit offhand. So one of the purposes of this project was, okay, so what is the trade-off? Can I get smaller quantization error? Can I get just smaller error in general? But at a trade-off of maybe losing some temporal precision. So that's what I'm going to show in demo 2. So instead of integrating for 5 cycles, I'm integrating for 15. So as we can see, we've got a 3x difference in speed, but we have much higher precision and less quantization error within each sample. So this is all well and good that I can see when I've got some macro scale changes in current, but I can also actually see much smaller changes. So for example, if I had a data dependent function here, where it's going to loop through each bit of this relatively randomly chosen value, and it'll do something different based on the value of each bit. It'll either call this first function or the second function. And these functions are just things in Python that I, through brute force, found lasted roughly the same length of 3-ish milliseconds. And with this, we can actually extract that input data just by looking at the actual binary values. You can actually see there's this macro change here. So the issue here is I've actually got a massive temperature change going on, I believe. So you can still see that there are some visible steps. But let's go over to some pre-captured data real quick. So this was when I had a much more stable temperature. That last one that we just saw come out has some massive temperature variation. And at first glance, this is a little hard to see what's going on. So I can manually add some grid lines. Then from here, this is the known correct value. So this is a little bit higher, so it's a 1. This is a little bit lower, so it's a 0. So these are the correct values, and you can actually get these out. I asked some friends and to inspect the data for me. These are the results they got. So we actually had one completely accurate result, one that was off by a single bit, and one that wasn't quite as good. But this is just showing that we can actually get some real data out of this system.